All right, so welcome to lesson 12. So far we've been learning differentiation techniques, and now we're ready to start applying those techniques to some concepts in real-world situations. Specifically in this packet, we're going to be looking at the physics example that looks at the position function, the velocity function, and the acceleration function. This content is coming from section 3.7 in your textbook. So our learning objectives for this activity are to find the velocity and acceleration functions if we're given position. We're also going to find out when an object is at rest, when it's moving in the positive direction or when it's moving in the negative direction. We'll find the total distance traveled as well as the displacement which is the net change in position. So it's where a particle, the difference between where a particle or an object started and where it finished its journey. And we'll also determine when an object is speeding up or when it's slowing down. Okay, so let's first do this warm-up. Suppose that the position of a particle in feet is given by this function, and here I did use p for position, but remember we use s a lot as well, s of t for the position where an object is at a moment in time. We're asked to find the average velocity of the particle over this time interval. So from 3 to 5 seconds, on average, how fast is the particle going and in what direction, right? We've thought about velocity as speed, but really velocity is allowed to be negative, which just means that that object is going in the negative direction. Okay? So our average velocity is the slope of this secant line. Slope of secant. Oops, and I can't spell. I still can't spell. Secant line. Okay, so our average velocity is going to be a change in position over change in time, specifically over this time interval. It is the position, and I'll use p because I used p up here. It's the position at time 5 seconds minus the position at time 3 seconds, all over 5 minus 3 seconds. All right. Bloop. Okay, and we can go ahead and plug into this function, but since I've given us the position function right here, and if you want, we could label these axes feet per second. Let's just go ahead and pull those ordered pairs. So p of 5 is 2.5 minus p of 3 is 4.5 all over 5 minus 3. That gives me a minus 2 over 2, which is negative 1. So what have we just found? We've just found that on average, between 3 and 5 seconds, the particle's velocity is minus 1. What are those units? Well, remember, this is a slope of the secant line. Slope is our rise over run. It's feet per second. So on average, the particle is going minus 1 feet per second. And you're saying, Lindsay, that makes no sense. How can you be going a speed of negative 1 feet per second? Well, that's not what velocity is saying. Velocity, because it's negative, that means that this particle is on its way down, which we can see. It's traveling in the negative direction, and its speed is the absolute value of this. It's traveling 1 foot per second and going down. Okay, so done. Now the instantaneous rate of change, the instantaneous velocity of the particle at 2 seconds, is asking me to find the slope of this tangent line. Slope of tangent. And we're asked to find that slope of that tangent line at a particular moment in time at t equals 2 seconds. Right? So boom. There's that 2. All right. So we do not need to estimate this anymore. We now know how to go ahead and take the derivative. The derivative of the position function will tell me the slopes of the tangent lines at any point on the curve. In other words, it'll tell me the velocity at any point on the curve. My position function is minus 1/2 t squared plus 3t. My velocity function, I'm going to use v for velocity, is the derivative of my position function, which we can go ahead and do. We love taking the derivatives of polynomials. I have one function of t plus another function of t. That's going to allow me to compartmentalize my thinking. I'm going to take the derivative of this part using power rule. We get minus 1/2 times 2 t to the power of 1, and then plus the derivative of 3t is just 3. So here we have it. My velocity function is minus t plus 3. And I specifically want the velocity at time t equals 2 seconds. So I'm going to evaluate this function at 2, plugging in a 2 everywhere I see a t, right there. And that gives me positive 1, right? And the units, again, feet per second, right? Don't get thrown off on the units. This is the slope. My position function, they told me, is a function of time in seconds, and we're measuring the height of this particle, the position of this particle in terms of feet. If you want to write seconds and feet here, you're welcome to do so. And done.